by the time you finish listening to this deep dive, the Frontier supercomputer will have chewed through enough electricity to power a small city for the entire duration of our conversation.
Yeah, it's a staggering amount of energy.
Over 20 megawatts
Yeah.
of just constant raw power. I mean, we're talking heavy industrial infrastructure
Yeah.
here, substations, massive cooling towers, all of it, just to keep the silicon from literally melting down.
Right.
And yet, the biological brain that is currently processing the words I'm saying to you right now, a system that handles real-time language parsing,
Mm.
spatial awareness, memory retrieval, it's running on what, about 20 watts?
Roughly 20 watts, yeah.
Yeah.
Less power than that little light bulb inside your refrigerator.
It's insane.
It really is the single most glaring discrepancy in modern technology today. Because we spent decades, optimizing the user experience of artificial intelligence.
Making it look seamless.
Exactly.
Yeah.
So when you type a prompt into that clean, minimalist little interface, it feels utterly weightless, like it's just pure thought floating around in the ether somewhere.
But that interface is really just an illusion, right? It's hiding this brute force industrial reality.
Oh, absolutely.
Okay, let's unpack this, because today we are tearing down that illusion. We're looking at a really fascinating technical paper by Lev Nemotin. He's the CEO of N5 Digital, and the paper is titled The End of the Digital Age Toward Analog Intelligence.
It's a provocative title.
It is. And our mission for this deep dive is to explore exactly why the current digital trajectory of AI is, frankly, colliding with a physical brick wall. And why the ultimate solution isn't just, writing cleverer code or pouring more concrete for larger data centers.
No, the solution they're proposing involves abandoning the very foundation of modern computing.
Which is wild to think about. We're
Yeah.
talking about moving away from digital bits and stepping into the continuous, kind of messy reality of analog systems.
The urgency of this paper really crystallizes when you look at the infrastructure shock that is happening right now in the industry.
Yeah.
The AI economy, it's not really a software phenomenon anymore.
What do you mean?
It's a heavy civil engineering phenomenon. We are talking about laying miles of high-tension power lines, installing these massive gas turbines, and securing water rights.
Water rights.
Yeah, for evaporative cooling. Tech companies have essentially unlimited capital to deploy toward this stuff right now, but, capital cannot rewrite the laws of physics.
Right, because the bottleneck isn't the balance sheet anymore. You can't just throw another $1 billion at a utility company and magically manifest a high-voltage transformer out of thin air.
Especially when those transformers have a 3-year manufacturing backlog.
Exactly. The paper actually notes that more than 60% of the data center capacity that was projected for 2025 and 2026 is either delayed or at severe risk.
Which is a huge problem for these tech giants.
I mean, you have companies who used to just design software and buy chips, and now they're having to act like regional power authorities. They're looking into on-site power generation and even attempting to restart decommissioned nuclear power plants.
And this reveals a fundamental architectural flaw in the whole system. We are essentially trying to solve a representation problem with a massive infrastructure build-out.
It's like, for you listening, it's like turning on the faucet in your kitchen to get a glass of water. But you don't realize that simply turning that handle is draining a massive overtaxed reservoir hundreds of miles away.
That's a great way to put it. When an AI company needs to train a larger model today, their primary strategy is just to string together 100,000 GPUs and feed them enough electricity to run a steel mill.
But the limiting resource of the intelligence age isn't human talent anymore, or even algorithmic design. The bottleneck is watts.
It always comes back to power.
Which brings us right back to that staggering comparison we started with, the 21 megawatt supercomputer versus the 20-watt human brain.
Yeah.
If our digital supercomputers require the power of an entire municipality to simulate just a fraction of the generalized intelligence that a human handles on 20 watts, it forces a pretty uncomfortable question.
It does.
Like, we built the entire modern world on discrete zeros and ones. If this digital method is so incredibly inefficient compared to nature, why did we ever choose a paradigm that turns out to be so metabolically punishing?
Well, if we connect this to the bigger picture, the digital age didn't conquer the world because it was a perfect mirror for nature. It won because it offered unprecedented control. It offered stability.
Right, because a bit is exact.
Exactly. The genius of the digital bit is its absolute rejection of ambiguity. In a digital processor, if a voltage sits above a certain threshold, the system strictly enforces a 1.
And if it's below, it's a 0.
Right. It violently shears away all the noisy, fluctuating, messy reality in between those two states.
It provides absolute exactness. I mean, you can copy a digital file a billion times, and the billionth copy is mathematically identical to the very first one. That exactness gave us, cryptography, global finance, the internet, formal logic.
It built the modern world. But that exactness comes with a massive hidden tax. Because the physical universe, it doesn't operate in binary. Reality is continuous.
What do you mean by continuous in this context?
Think about temperature or sound waves or the chemical gradients in your brain, the changing light in a room. None of these things naturally exist as discrete, quantized, perfectly separate states.
They flow.
Exactly. So to make a digital machine process the real world, you are forcing it into this incredibly expensive detour.
Right. You have to take a smooth, continuous wave of reality and slice it up into millions of tiny, discrete binary fragments.
Yes, and then you run those fragments through billions of logic gates.
Just shuffling them back and forth between memory and processors over and over, just to stitch them back together on the other side into something that mimics a fluid output.
It's exhausting just talking about it.
Here's where it gets really interesting for me, and I try to picture it like this. It's like trying to build a perfectly smooth, sloping curve out of microscopic, jagged Lego bricks.
No, that's a good analogy.
Right. If you stand far enough back, your eye might perceive a smooth curve. You look at it and say, oh, that's a nice slope. But the amount of friction, the sheer mathematical effort required to force those millions of jagged little blocks to act like a continuous line is immense.
And that friction is exactly what the author of the paper describes as heat as a philosophical signal.
Okay, wait, I love that phrase. Heat as a philosophical signal.
It's brilliant. Heat in a data center is not just an engineering annoyance, It's not just something to be routed away with liquid cooling loops so the servers don't crash.
What is it?
It is the physical universe actively telling us that our computational abstraction is fighting reality. A digital machine operates with brutal exactness, yes, but it completely lacks grace. Nature is graceful.
Like a pendulum. A pendulum doesn't calculate binary math to swing back and forth.
Exactly.
It just swings. It behaves according to the laws of physics embedded in its mass and the gravity of the Earth. It's not running software. Or think of a glass lens bending light. It doesn't run a discrete Fourier transform algorithm.
Right, crunching numbers through millions of transistors just to figure out the angle of refraction.
No. The physical properties of the glass perform the computation instantly, gracefully, and with literally zero software overhead.
Which brings us to the core thesis of Moten's paper, Neural Vector Architecture, or NVA.
Right. Let's get into NVA.
The proposal here isn't to just build a slightly more optimized digital processor. This is a fundamental paradigm shift toward analog intelligence.
This is moving from bit management to concept management.
Precisely.
Let's get into the mechanics of this, though, because I know when a highly technical audience hears the word analog, the immediate reaction is usually skepticism.
Oh, for sure.
We immediately think of, like, vinyl records degrading or those massive analog computers of the 1960s that drifted wildly if the ambient room temperature changed by 3 degrees.
Right. The drift was a huge problem.
But NVA fundamentally changes the primitive unit of computation. Instead of 1 or a 0, the basic building block becomes a continuous physical state, a vector.
Wait, so is this just trying to build an artificial, literal, biological brain in silicon?
No, and it's really important to draw that distinction. NVA is neural, yes, but it is not strictly neuromorphic.
Okay, break that down for us.
Well, the trap of neuromorphic engineering is treating the human brain as a literal circuit diagram that just needs to be copied and printed onto silicon. The paper uses a really classic analogy here, early aviation.
The flapping wings.
Exactly. When humans first tried to fly, engineers built machines with flapping wings because, well, that's what birds did.
And it turns out flapping wings are terrible for carrying heavy payloads at Mach 2.
Right. Jet engines don't look anything like birds, but they master the underlying principles of aerodynamics much better for our specific needs.
So we shouldn't blindly copy biology neuron by neuron. Right, because brain imitation often becomes more of a metaphor than actual engineering. We don't want to copy biological hardware blindly. We want to extract the underlying efficiency principles.
Like what?
Like co-locating memory and processing.
Okay.
In a standard digital neural network, You are constantly battling something called the von Neumann bottleneck.
Right, the data shuffling.
Exactly. You have to physically fetch a weight from memory, move it over to the processing unit, do the math, multiply it, add it to an accumulator, and then send it all the way back to memory.
And for a modern AI model doing trillions of matrix multiplications every second, you are spending a massive percentage of your power budget just moving data back and forth across microscopic wires.
It's hugely inefficient.
Yeah.
But with NVA and analog computation, you just start shuffling the data. You use the physics of the materials themselves to do the math.
This is the part that blew my mind.
Yeah, so if you want to multiply two numbers, you don't use a bunch of logic gates. You just pass a specific voltage through a material that has a specific electrical resistance. Thanks to Ohm's law, the resulting current is instantly the product of those two values.
It just happens.
It just happens. And if you route several currents onto a single wire, Kirchhoff's laws dictate that they naturally sum together.
So the physics naturally does the matrix multiplication instantaneously, at the speed of light, natively right there in the hardware.
Yes. In NVA, memory and compute are not physically separated. They occupy the same space, just like synapses in a biological brain. A biological synapse stores the memory of its strength and performs the computation at the exact same time when a signal passes through it.
So it's computing with the physics rather than fighting against it.
Exactly. But of course, we do have to address the elephant in the room.
Analog noise.
Yes, analog noise.
Because we abandoned analog computing decades ago, precisely because it was imprecise. I mean, in an analog crossbar array, no two resistors are manufactured perfectly identical down to the atom.
It's physically impossible.
Right. And if the temperature of the chip fluctuates, the resistance fluctuates. So if my self-driving car's vision system is relying on analog matrix multiplication and the chip heats up in the sun, does it suddenly miscalculate the vector and forget what a stop sign looks like?
That is the classic fatal flaw of legacy analog systems. But NVA does not pretend to solve it by demanding mathematically perfect analog manufacturing. Instead, it solves it architecturally through a hybrid approach.
Okay, hybrid approach.
The future isn't purely analog, it's a symbiotic system.
A digital skeleton with an analog muscle.
I love that phrasing. Yes.
Yeah.
You still need digital logic for exactness, where it really matters. The digital layers are going to handle the rigid tasks: data routing, memory storage, cryptography, error correction, interfacing with the internet.
Just structural skeleton.
Exactly. But the heavy lifting, the trillions of dense matrix multiplications required for pattern recognition, deep learning, and continuous control, all of that is handed off to the analog cores.
The muscle. You know, this isn't a war between paradigms. The paper makes a brilliant historical comparison here. When the automobile was invented, it didn't instantly abolish the roads built for horses.
No, they shared the infrastructure.
Right. Cars integrated into the existing network and gradually took over the heavy and long-distance workloads until the infrastructure evolved completely around them. NVA isn't going to just delete digital computing.
Not at all.
It's going to intercept the massive, power-hungry AI workloads where digital architecture is currently tearing the power grid apart.
And regarding your point earlier about analog noise and temperature drift, there is a fascinating mechanism at play with modern machine learning. We now actually have the capability to let the software learn the quirks of its own physical hardware.
Wait, really? The AI basically trains itself to compensate for the manufacturing defects of the specific chip it's sitting on.
Yes. Instead of forcing the hardware to be perfectly pristine, the system expects variation. It self-calibrates. But even more profound is how the paper reframes noise entirely.
Noise is a feature, not a bug.
Exactly. In strict digital logic, a flipped bit is a catastrophic bug that crashes your entire program. But in biological systems and in analog, AI noise is actually an evolutionary advantage.
This is a huge point, especially for anyone listening who understands how AI models actually train. Because when an AI is learning, it's essentially rolling a ball down a massive, multidimensional, hilly landscape, right?
Right, trying to find the absolute lowest valley.
Gradient descent.
Exactly.
But the problem is, if the math is too precise and too rigid, the ball can easily get stuck in a shallow ditch, a local minimum, and think it has found the bottom of the entire landscape.
And that's where analog noise comes in. The inherent physical fluctuations in an analog system provide this constant low-level stochastic jiggle.
It jiggles the ball.
It continuously bumps the system, preventing it from getting trapped in those rigid, suboptimal solutions. This natural variation allows for probabilistic thinking. It gives the AI a way to explore broader solution spaces.
which is exactly how biological evolution relies on random mutation to adapt to complex environments.
Exactly.
So if we pull all of these technical threads together for you, escaping the memory wall, computing with physics, leveraging a hybrid architecture, and using noise as a feature, what does this actually look like deployed at scale?
That's the real question.
Because right now, powerful AI is effectively tethered to a warehouse. If my home internet connection drops, the highly advanced smart assistant in my kitchen becomes an incredibly expensive paperweight because it can't talk to a multi-gigawatt server farm in Virginia.
The strategic endgame of NVA is pushing high-performance AI to the edge.
The edge meaning local devices.
Right. If you can run massive neural networks on analog chips that draw a fraction of a watt instead of 1,000 watts, the intelligence becomes localized.
That's huge.
We are talking about running advanced adaptive AI natively inside autonomous robotics, medical clinics, remote industrial sensors, household devices, without needing a constant cloud connection.
The strategic implications of that for national security are massive.
Yeah.
I mean, think about it. A country whose entire artificial intelligence capability relies on a handful of hyperscale data centers is incredibly fragile.
Well, highly vulnerable.
Those facilities are highly visible, they are completely dependent on an overstressed power grid, and they require massive water reserves. A single grid failure or a targeted disruption cripples the AI capabilities of millions of devices instantly.
Conversely, a society built on decentralized, low-power analog infrastructure is deeply resilient. It completely removes that fierce competition for energy.
Right, you no longer have municipalities and hospitals fighting with tech conglomerates over who gets the electricity from a local power plant.
The intelligence just operates locally, efficiently, and independently.
Now, I know some of you listening might be wondering about the other massive computing paradigm shift that's constantly in the news. Quantum computing.
Quantum.
Yeah. If energy and processing power are the bottlenecks here, doesn't quantum hardware eventually sweep in and solve all of this?
Well, Nemotin addresses quantum directly in the paper, and he draws a very sharp boundary.
What's the boundary?
Quantum computing is a miraculous technology for highly specialized, specific mathematical domains, things like simulating molecular chemistry or breaking encryption. But it is fundamentally unsuited for general-purpose AI deployment.
Because of the physical requirements.
Yes. Quantum hardware currently requires extreme cryogenic environments. You have to isolate the qubits near absolute zero.
Which means you aren't putting a cryogenic dilution refrigerator into a self-driving car.
Yeah.
Or a smart thermostat.
Exactly. Quantum solves extraordinary, isolated problems. Analog intelligence is engineered to solve the ordinary miracle of everyday cognition. It is designed to exist in room temperature, embedded in the messy physical reality right alongside us.
So, what does this all mean? To synthesize this entire journey for you, the ceiling of the digital age is not a lack of algorithmic innovation or coding talent. It is a very real physical wall of heat and thermodynamics. We have spent half a century forcing the continuous, graceful reality of the physical world into rigid, jagged digital boxes. And yeah, that abstraction gave us incredible capabilities, but attempting to scale that method up to artificial general intelligence is quite literally melting our infrastructure.
The path forward requires us to stop fighting physics.
Yeah.
AI has to evolve from manipulating digital bits to managing analog concepts via this neural vector architecture.
Embracing the natural grace and efficiency of physical systems.
Exactly. We have built the current iteration of AI inside an artificial bubble of limitless abundance. The foundational assumption of the tech industry has always been that there will simply be more. More power lines, more data centers, more silicon.
Just build it bigger.
Right. But biological intelligence, which is the only true general intelligence we possess, draws its incredible capabilities precisely because it evolved under severe, unforgiving metabolic constraints.
A biological brain must compress information efficiently, and it has to generalize across domains because it simply cannot afford the caloric energy to do brute force calculations. It must be efficient to live.
So if we truly want artificial intelligence to reach its highest, most sophisticated potential, perhaps the machine shouldn't be allowed to demand a private power plant.
That's a profound thought.
Perhaps true, elegant intelligence can only emerge when a system is forced to think within the strict energy budget of life.
That concept leaves us with a truly fascinating, provocative implication to consider on your own. We typically measure the advancement of a civilization by how much raw energy it can harness.
Like the Kardashev scale.
Exactly, the Kardashev scale, where a highly advanced civilization is defined by its ability to harvest the total energy of its planet and eventually the total energy of its local star, building Dyson spheres and all that.
Right. Massive energy consumption.
But if the ultimate endpoint of complex intelligence is actually mastering biological-level analog efficiency, perhaps our entire metric is backwards.
How do you mean?
Well, maybe the most advanced, hyper-intelligent civilizations in the universe aren't building galaxy-spanning megastructures that blot out stars. Maybe they are entirely invisible to us, quietly running profound, universe-simulating intelligence on the wattage of a dim light bulb. Wow. So next time you drop a prompt into an AI and wait for the magic to happen on your screen, think about the heavy machinery burning on the other end and ask yourself what true efficiency will really look like. Thank you so much for joining us on this deep dive.